Welcome back. We're going to start in on chapter 3 today. Chapter 3 is going to talk about curve sketching and all the different things that we can do with a graph. We're going to do a lot of graphing in chapter 3. We're going to start with, though, Extrema. And what is an Extrema and how do we find it? So an Extrema is the highest or lowest value of a function on a given interval. Relative maximum, relative minimum, we've seen these words before. We started with them in Algebra 2. We looked at a graph. We saw where the high points or the low points were. Same thing here. Relative maximum is going to be the highest point on a given interval. Relative minimum is going to be the lowest point on an interval. And what we want to see today, though, is how that calculus is going to play into these relative maxes and mins. Because we're not going to necessarily have to use that calculator to be able to graph it. We're going to be able to use our knowledge of calculus to be able to find our relative maxes and our mins. So if we notice here from Algebra 2 in pre-calculus, you saw that we had a relative max at this point, and we had a relative min at this point. Well, we also now want to go ahead a little farther, and let's look at the tangent lines. If we notice the tangent lines to the left of this relative max, all of these tangent lines have a positive slope. On the other side of this relative max, we have negative slopes. When we come from the left to this relative min, again, all negative slopes. But as we come out of that relative min, we have positive slopes again. So we are going to see that we go from a positive slope to a negative slope. So we are increasing positive, and then decreasing negative. It's going to change at this relative max. What do we notice that happens at the relative max with our tangent line? Well, we have a horizontal tangent line, which we've spent a little bit of time in chapter 2 finding that horizontal tangent line. Likewise, in this relative min, we go from a negative to a positive, which we're going to have that relative minimum occurring at that horizontal tangent line. We're also going to introduce those words global. Global's max and min is going to be the absolute maximum and minimum overall on our graph. So think globally, think largely, think the whole thing. So we talked about where the graph increases and decreases, increases. That's where our tangent lines were equal to 0. So I introduced a theorem here. It's the extreme value theorem. And it tells us that if we're continuous on a closed interval, then f is going to have a maximum and a minimum value on that interval. So we're going to have a relative max and a relative min. So if f is not continuous on a closed interval, then we don't necessarily know that there's a maximum or minimum value going to exist. That's kind of important. If it's not continuous, we don't know necessarily if a maximum or minimum value will be in existence. To find our extrema, one, we're going to find our critical numbers. Critical values. We've talked about critical values in the past, and these are things where things are going to happen, values where things are going to happen. So how do we find our critical values in calculus? Well, we're going to take the derivative and set it equal to 0. We're going to take any of the endpoints as well. So we had this interval a to b. So these are going to be my endpoints that I'm talking about. We're also going to be talking about where the function is not differentiable. And that's going to be where at a cusp, or if we have a sharp turn. One example, remember if we had an absolute value, we're not differentiable at that vertex. So we're going to find the value of each of our critical points, where our derivative is equal to 0, or endpoints in any cusp or sharp turns. The largest value is the absolute max. The smallest is the absolute min. So let's go ahead and look at an example here. We are going to find the extrema for this function. X to the third minus 3/2 x squared on negative 1, 2. If I go ahead and find my derivative, f prime of x, this is going to give me my critical values to start. I'm going to set that equal to 0 so I can factor out a 3x, x minus 1. So a little bit of algebra 2 here. So we get x equals 0 and x equals 1. I'm interested in the values, these values 0 and 1 and negative 1 and 2. So I'm going to find f of negative 1, f of 0, f of 1, and f of 2. And what I would suggest, since you have the calculator at your disposal, I would go ahead and use that, but I would also be able to do this by hand. So I'm going to take that negative 1, I'm going to plug it into my original function, Again, if you have your calculator, I would go ahead and put it into a table, which is what I'm going to do right now. So I have x to the third minus 3 halves x squared. And I'm going to do a table setup. I'm going to do an ask on my independent variable. I'm going to type in -1. It's going to be a -2.5. If I plug in 0, it gives me 0. Of course, plug in 1, we should get -1/2. And then if I plug in 2, I get 2. Again, calculator makes this go a little quicker. I do want to see the work. I don't want you just to put it in the calculator and say, oh, here it is. So I do want to see the calculus behind it. So our relative maximum is going to be the highest point here, which is going to be here at 2. So we have a relative max at 2, 2. And our minimum is going to be up here, so we have a relative min at -1, -2.5. Now, some of the verbiage that we're going to see here. So we could say the relative max occurs at x equals 2, or the point 2, 2. We also have a relative max. We could say the relative maximum is 2 from our y value. Likewise, for the relative min, we have a relative min occurs at x equals -1, or the point -1, -2.5. But the relative minimum is -2.5. So some verbiage that we're going to see, I'm not going to do this on all of them, and I don't expect you to write all of this, but be able to recognize what the verbiage is talking about. We're going to go ahead and find the extrema then on x squared minus 2 minus cosine of x on the interval -1 to 3. So for our next example, so derivative of x squared gives us 2x, derivative of negative cosine is going to be positive sine, that's a bad looking s, isn't it? Bad sine of x. I'm going to go ahead and set that equal to 0. If I set that equal to 0, we're going to go ahead and, what do we got? Oh, 2x plus the sine of x. So we can go ahead and put that in our calculator. I'm going to have to put that in the calculator because I don't want to solve that. 2x plus the sine of x. Make sure your mode is in the correct mode, which is going to be radians. So if I go ahead and graph that, pull that up there. There we go. So notice here we're looking at that point where we cross the x-axis. So I can go ahead and find that by doing my trace to find my zeros. I'm going to type in -1 to 1, and I'm going to guess, so it's at 0, 0. So 0, 0 is definitely on that interval. So we're going to go ahead and find f of -1, find f of 0, and find f of 3. Again, we're going to go ahead into our calculator, type in our x squared minus 2 minus the cosine of x. To our table, we're going to type in -1, which gives us -154. Make sure that's, oh, yep, that's 0, that's good. 0 is going to be -3, and then 3 is going to be 799. Make sure that's all values. So 799 is going to be our rounded value. So here's our relative max and our relative min. This is a point, yeah, and our relative min. There's going to be our extrema for that function. We can do this with several more examples. I'm going to do 2 more here, and then we'll look at a couple of AP questions here. I'm going to throw that one out. So derivative 1 over x minus 2. So I would suggest that we bring that to the top as a negative exponent. We can go ahead and find our derivative. F prime of x is going to equal the negative of x minus 2 to the negative second times 1. So we get the value of -1 over x minus 2 squared. If I set that equal to 0, multiply that over, I get nothing. But we also have to be very careful because we know that we have an asymptote at x equals 2. So x equals 2, there's going to be it's going to be discontinuous. Couldn't think of the word there. Discontinuous, so it's non-differentiable. So we have to worry about that x equals 2. However, if we notice our interval is 0 to 1. Since it's 0 to 1, then x equals 2 does not apply on that interval. So we're not interested in that 2. Isn't that nice? So we're going to go ahead and find f of 0 and f of 1. If I plug in 0, we get negative 1/2. If I plug in 1, I get negative 1. So our highest point is going to be here, so we have a relative max, and negative 1 is going to be our relative min. We can go ahead and find 2x minus 3x to the 2/3. Our derivative is going to be 2 minus 2/3 times 3 gives us 2x to the negative 1/3, setting that equal to 0. So f prime of x, well, we don't need that, do we? So go ahead and subtract your 2 over, divide by 2, we get x to the negative 1/3 equals 1. We can write this as x to the 1/3 equals 1. So x is going to equal 1. X equals 1 is going to be a critical value. It's on the interval negative 2 to 2, so we're going to go ahead and find all those values. Go into your calculator. Again, we're going to type that original function in. We have 2x minus 3x to the 2/3. Do our window or our table, so we get negative 2, which is negative 8,762. R1, which is going to be negative 1, and 2 is going to be negative 0.7622. So our relative max, looks like here is going to be f of 2, and our relative min is going to be the negative 872 at negative 2. Alright, and the last problem I want to look at is kind of an AP question, and how can we determine if the graph has a minimum on the open interval a to b. So if we notice here, the graph we have open-ended on this part of the graph, but then at this part of the graph we have a closed, an inclusive, and then an exclusive. So do we have a minimum value on this open interval? And in this case, we don't have a minimum value. We get closer and closer and closer to whatever this value here is, but we don't know exactly what it is. So our minimum value doesn't exist. So there is no minimum value. But on this example, we have an exclusive end to an inclusive and then two exclusives. Do we have a minimum value here? And yes, we do have a minimum value here because it's defined at that low point. It's not continuous, but we know that we're going to have a minimum value there. So yes, this one would have a minimum value. And that gives you kind of an idea of what we're going to see maybe as an AP style question. So this is non-differentiable at this point here, makes us, and then we're exclusive in this area, so we have a no minimum value. Where this one is still, it's non-continuous, so it's non-differentiable at this point, but we have that minimum value. So hopefully that gives you an idea of our extrema and being able to find them. Good luck and have fun with them.